Boston Housing Kaggle Challenge, Linear Regression Introduction. Welcome to your beginner-friendly machine learning project. Today, you will discover how to use the Boston Housing Dataset. You will learn how to set up your data and build a basic linear regression model. This challenge helps teach the foundations for predicting property prices. No previous machine learning experience is needed. Running the cell now. What is the Boston Housing Dataset? This dataset contains housing information for suburbs in Boston. It was designed for regression tasks, where you predict house prices. Each row is a suburb. The columns describe things like crime rate and room numbers. The goal is to predict the MEDV column, which means median house value. This is a famous real-world benchmark for beginners to learn regression. Running the cell now. Why linear regression? Linear regression is a simple and popular way to predict numbers. It helps you understand how features relate to target values. This is great for building your intuition before you try more complex methods. Running the cell now. We suppress warnings to keep the output clean and less confusing for beginners. Import NumPy as NP. We set the random seed to 42 for reproducibility. Running the cell now. Here, the code sets up a clean and reproducible environment by fixing the random seed and suppressing warnings. While there's no direct output yet, this step is crucial to ensure consistent results in our linear regression experiments and to keep the focus on learning the core concepts without distraction. We now set up our data using the Boston Housing Dataset from a safe public source. We import pandas, which is a popular Python library for data tables. We provide the CSV file's URL so pandas knows where to download the data from. The dataset is read into a data frame called df. Think of this as a table in Excel. We print the shape of the data so you know how many rows and columns there are. We also preview the first 3 rows. This helps you understand what the data looks like. Running the cell now. Here, we load and inspect the Boston Housing Dataset, consisting of 506 rows and 14 columns, each representing features like crime rate, average rooms, and the target median home value (MEDV). Noticing the variety and scale of these columns helps us understand the data we'll model with linear regression to predict MEDV based on these features. This foundational step sets the stage for exploring how each feature relates to home prices. Next, we check whether the data has any missing values. Missing values can cause problems for machine learning models. Running the cell now. Here, we are checking for missing values in each column before building our linear regression model. Notice that all columns show 0 missing values, meaning our dataset is complete and ready for analysis. This step ensures our model can confidently learn relationships without incomplete data interfering. Let us explore the data structure. Info shows all column names and their data types. You will also see if any columns are not numbers. Running the cell now. This output shows the structure of our dataset, with 506 rows and 14 columns representing different features and the target variable, MEDV. Notice the mix of float and integer types, all without missing values, which is ideal for applying linear regression to understand how these features relate to housing prices. This foundational step ensures we know what data we're working with before building our model. We create a summary of the data with one command. Describe shows count, mean, minimum, and maximum for each column. Running the cell now. This statistical summary gives us a snapshot of all the features in our housing dataset, showing counts, means, and ranges. Noticing the wide range and variation in columns like crime rate, and RM, average rooms, helps us understand the data's scale and distribution, which is essential before applying linear regression to predict house prices. This step builds intuition about which features might have stronger relationships with the target. Exploring and understanding features. Each column in the dataset is called a feature. Features like crime rate, or RM, average number of rooms, can affect house price. The MEDV column is your target. That is the value you want to predict. Take some time to scan the feature names and use descriptions online for more details. Running the cell now. We start by plotting the target variable to understand its distribution. We import the matplotlib library to make the plot. We set the size of the plotting window to make it clear and readable. We draw a histogram to show how often different median house values occur in the dataset. We add a title to explain what the plot represents. We label the x-axis to show that it represents the median house value in thousands of dollars. We label the y-axis to show the frequency of each value range. Finally, we display the plot for us to see. Running the cell now. This histogram shows the distribution of the target variable MEDV, which represents median house values in thousands of dollars. Notice how the values are spread, with most houses clustered around certain price ranges, and any skewness or gaps that might affect prediction. Understanding this distribution is key before modeling, as it highlights typical prices and potential outliers in the data. To build a model, you must tell Python what you want to predict and what you want to use for prediction. Features are everything except the target column. The target is usually called Y. Running the cell now. Here, we've separated the features and target variable to prepare for analysis and modeling. Notice that X contains all the columns except MEDV, which is saved separately as Y because it's the value we want to predict. This step is crucial for exploring how these features relate to housing prices in later lessons. We split our data into a training set and a testing set. The training data teaches the model. The test data checks if the model can handle new and unseen cases. We use 20% of the data for testing. Setting random_state equals 42 means you always get the same split for repeatability. Running the cell now. This output shows the dataset split into training and testing sets, where we have 404 samples for training and 102 for testing, each with 13 feature columns. Notice how the split keeps all features intact, ensuring the model learns from a substantial portion of data before being evaluated. This step is crucial for building reliable predictions on unseen data using the features we've explored. What is linear regression? Linear regression tries to draw the best line through your data. It predicts a number value, for example, a price, based on the features. This is called a supervised learning method because you show the model what the right answer is during training. Linear regression is easy to use and is often the first model you try for continuous predictions. Running the cell now. This section builds and trains a linear regression model. We import the linear regression class from the scikit-learn library. We create an instance of the linear regression model called LR. We train the model LR using the training data features and target values. Running the cell now. This output shows that the linear regression model has been successfully created and trained using the training data. The simple linear regression printout confirms the model object is ready to make continuous predictions on new data. This step is key because it reflects the supervised learning process where the model learns the relationship between features and target values. We ask the trained model to predict home prices for cases it has not seen before. Y_pred will contain the predicted prices. Here, we print the first 5 predictions for inspection. Running the cell now. Here, the model predicts continuous numeric values for the first 5 test samples, demonstrating how linear regression estimates outcomes based on the input features. Notice these predictions are decimal numbers, reflecting the model's effort to fit a line that best captures the relationship in the data. This output illustrates the core idea of supervised learning, using known data to predict new values. This comment explains that we will evaluate the model using mean-squared error and R2 score. We import the functions mean_squared_error and R2_score from scikit-learn.metrics to use for evaluation. Calculate the mean-squared error, MSE, between the true values y_test and the predicted values y_pred. Calculate the R2 score between y_test and y_pred to see how well the model fits the data. Print the mean squared error rounded to 2 decimal places to show average prediction error. Print the R2 score rounded to 2 decimal places to indicate the proportion of variance explained. Running the cell now. This output shows how well the linear regression model predicts the test data. The mean squared error, 24.29, measures the average squared difference between predicted and actual values, while the R2 score, 0.67, indicates that about 67% of the variance in the target is explained by the model. These metrics help you understand the model's accuracy and fit, which is crucial for evaluating how good your line is at predicting new data. We start by describing what this plot will show: predictions versus true values. Set the figure size to make the plot clear and easy to see. Create a scatter plot of actual versus predicted values, coloring points purple with some transparency. Draw a dashed diagonal line that represents perfect predictions, where predicted equals actual. Label the x-axis to indicate it shows the actual median values. Label the y-axis to indicate it shows the predicted median values. Give the plot a title that summarizes what is being displayed. Display the plot on the screen. Running the cell now. This scatter plot compares the actual median home values, MEDV, to the predicted values from the linear regression model. Notice how the purple points cluster closely around the dashed diagonal line, which represents perfect predictions, indicating the model's ability to approximate true values. This visualization helps evaluate how well the linear regression has learned the relationship during training. How to improve results. Try using only some features or adding new ones. Experiment with different machine learning models. Tune the model's parameters, these are called hyperparameters. Clean or transform the data for even better accuracy. This is what Kaggle competitions are all about. Small improvements can make a big difference. Running the cell now. Introduce the idea of making your own prediction by inputting custom values for house features. Mention that the following code is a simple example intended for beginners. Print a message to announce that the program will predict house price based on inputs. Ask the user to input the number of rooms in the house. Ask the user to input the local crime rate as a numeric value. Ask the user to input the age of the house in years. Create a default input vector using average values from the dataset. Replace the default number of rooms with the user's input. Replace the default crime rate with the user's input. Replace the default house age with the user's input. Use the trained model to predict the house price based on the updated inputs. Print out the predicted median house price in thousands of dollars. Running the cell now. This output shows the result of making a custom house price prediction based on user inputs for rooms, crime rate, and age using the trained linear regression model. Notice how the code replaces these specific features with your values while keeping others at their average, highlighting the impact of just a few selected features on the prediction. This interactive example demonstrates the lesson's point about experimenting with feature values to see how they influence model results and improve understanding. Mini project: try changing inputs several times and see how much the prediction shifts. Try setting rooms to 4, 6, or 8 and see what happens to price. Can you find a set of values that gives a high predicted price? If you enjoy learning with us, make sure to subscribe and hit the like button so you do not miss future lessons. We start by explaining that we want to see the coefficients to understand feature influence on price. Here we create a series mapping each feature name to its linear regression coefficient. Next, we sort these feature importances from highest to lowest to see the most influential features first. Finally, we print the sorted feature importance values to observe which features affect the price most. Running the cell now. This output shows the coefficient values from a linear regression model, indicating how each feature influences the predicted price. Notice that RM, average number of rooms, has the strongest positive impact, while the NOx, nitric oxide's concentration, has a large negative effect, suggesting these features are key drivers in the model. Understanding these coefficients helps guide feature selection and engineering to improve model accuracy, aligning with the lesson's focus on experimenting to boost results. We are about to create a plot showing the top features. This line plots a bar chart of the top 5 feature coefficients in green. Here we set the title of the plot to explain what it shows. This labels the y-axis to clarify the values represent coefficient magnitude. This labels the x-axis to indicate the feature names are shown. Finally, we display the plot so it appears on the screen. Running the cell now. This bar chart highlights the top 5 features with the strongest positive influence on the model's predictions, shown by their coefficient values. Notice how the height of each bar reflects the magnitude of impact, guiding you on which features might be most valuable to focus on or engineer further. This helps you understand which inputs the model relies on, a key step in improving or tuning your model's performance. Recap and next steps. You just completed your first end-to-end linear regression project for house price prediction. You learned about regression, metrics, features, and evaluating your session. The skills here translate to many other prediction tasks. Try more datasets, experiment with features, or try tree-based models for even better results. If this helped, please subscribe and share this video so more beginners can join. Happy coding and enjoy your data journey. Running the cell now.